Hello the internet, I'm David Stephenson from Warwick University and I'm going to be talking about a hybrid method for the design of multi-scale nanofluidic networks. But first I'd like to acknowledge some of my co-workers in this: Duncan Lockerby from University of Warwick, Matthew Borg from Strathclyde and Jason Reese from Edinburgh. I'd also like to acknowledge the EPSRC for funding this work. So when I talk about a multi-scale system, what I'm referring to is a system which exhibits a high degree of scale separation. Now, for networks which are comprised of high aspect ratio channels, such as the one pictured, the length scale in the streamwise direction is much larger than the length scale in the transverse direction. So as the channel height approaches the nanoscale, this presents a problem. A traditional computational fluid dynamics approach will become highly inaccurate because the continuum and local thermodynamic equilibrium assumptions of the Navier-Stokes equations will break down as the scale of the system approaches the molecular scale. And broadly speaking, this happens because as the length scale decreases, the surface to volume ratio increases, and this leads to the flow behavior being dominated by the wall-fluid interaction, while the bulk fluidic region, which can accurately be treated as a continuum, becomes negligibly small. So a continuum approach is highly inaccurate, but on the other hand, a full molecular simulation is computationally intractable because of the large length scale in the streamwise direction. So what we need to use is a so-called hybrid method, which combines the accuracy of a molecular solver with the efficiency of a continuum approach. And the hybrid method we use we call the internal flow multiscale method, or IMM for short. And what this method does is it exploits that scale separation between the gradually varying macroscopic processes which occur along orders of magnitude similar to the channel length in the streamwise direction, and the rapidly varying molecular processes which occur on orders of magnitude similar to the channel height in the transverse direction. And this means that we don't need to obtain a molecular resolution along the entire length of the channel, and instead periodic microelements, which are just individually simulated molecular subdomains, are placed at regular intervals along the channel length, with the spacing between them sufficient to resolve any variation in geometry. However, each microelement does need to cover the entire channel height in order to accurately model the molecular processes, and in particular to capture the wall-fluid interaction which dominates the flow behavior. So these microelements are linked together through a macro model which is simply the one-dimensional equations for mass and momentum conservation. And these equations don't require any constitutive relations like viscosity, and they don't require any boundary relations like velocity slip, because all of that is inherently modelled within each microelement simulation. So the only information that actually needs to be passed between the microelement and the macro model is that of macroscopic fluxes. And in the case of isothermal and steady state flows, which is what we're looking at in this work, the only macroscopic flux we're concerned with is the mass flow rate. So the mass flow rate is measured in each microelement, and the measurements are used to evaluate continuity errors within the macro model. So the macro model then responds by attempting to reduce these continuity errors for the next iteration of microelement simulations by setting new targets for pressure and pressure gradient at each microelement location along the length of the channel. So in each microelement, the target pressure is achieved by adding or deleting molecules until a desired mean density is reached, and an external body force is applied to all molecules within the microelement such that this produces a momentum flux which is equal to the pressure gradient we wish to induce at that location. So that's all well and good, but what if there is no scale separation that can be exploited? If you consider this more complicated network below, there are a number of bends in it. There's a rapid expansion and contraction, and on the left hand side there's a bifurcation. Now clearly, if you wanted to use microelements in the manner I described before, then you need to have them spaced very closely together to be able to accurately model the rapidly changing geometry. And this becomes very inefficient. So we don't do that. Instead, we use a method which we call the General Networks Internal Flow Multiscale Method, or GenIMM for short. And this method works by decomposing the network into smaller components, each of which is simulated using a molecular solver. So there are two types of components. Firstly, junction components, which are these elements of rapidly varying geometry which cannot exploit scale separation and must be modelled in their entirety by the molecular solver. And then there are channel components, which can be simulated using smaller microelements, as described earlier. And as described earlier, components are linked together through simple macroscopic conservation laws at the internal inlet-outlet boundaries, which form the border between adjacent components. But we don't yet have enough information to solve for all the macroscopic system properties. There are two things we further require. Firstly, we require a set of user input generalized constraints. Now usually, if we're going to use the GenIMM as a simulation tool, then these constraints would be the geometry of the network, that is the height of the network at each boundary and the length of all the channel components, and we'd also require the pressures at the external boundaries, which are the global inlets and outlets of the network. Now if these are the generalized constraints, or the boundary conditions as we'd call them, then the output of the hybrid method is the mass flow rate through the network and the value of pressure at all the internal boundaries along the network. However, when using the GenIMM as a design tool, we enable the mass flow rate or the values of pressure at internal boundaries to be specified as generalized constraints. And this then allows for the geometry of the network or the values of pressure at external boundaries to be the output of the hybrid method. So the GenIMM, when used as a design tool, provides speed up over a full molecular simulation in two main ways. Firstly, by not having to simulate the channel components in their entirety, and secondly, by not having to use a trial and error process to determine the correct geometry which will yield the desired macroscopic system properties. Then the second thing we require is an iterative refinement procedure which will minimize the continuity errors between components and converge the system towards the generalized constraints I just mentioned. So each component will have an equation similar to this, which basically states that the mass flow rate through the component will vary monotonically with the change in pressure drop over the component, and it will vary according to some proportionality constant k. And in turn, k is then related to some unknown prefactor omega, and the cube of the component height at its inlet and outlet boundaries, here with the subscripts I and O, and this is using basic flow circuit rules. So the unknown prefactor can either be determined through some pre-simulation, which could be using a molecular solver, or could just be using some CFD solver, or it could just be from basic intuition of the particular network that you're studying. So in equation 1, the terms on the right hand side are measurements from molecular simulations at the previous iteration, and the terms on the left hand side are then the targets for the next iteration. So you can see that when the target pressure drop for the next iteration is the same as that measured from the previous iteration in the same component, then the target mass flow rate will also cease to be updated from the previously measured value. One more thing to note is that the exact value of omega and of k aren't that important, and this is because firstly you can update the values with each iteration as you get better information about the system you're trying to model, and secondly they don't actually affect the final converged result of the GenIMM solution, they only affect the convergence rate. So one final thing we need is some iterative equation of state which relates the target mean density in the component to the target mean pressure in the component, and this allows us to deal with compressibility effects in the fluid. So now let's move on to look at some cases and some results. So despite our method being applicable to more complicated networks, we choose to validate using the GenIMM as a design tool by considering a serial network which is comprised of a straight channel connecting two reservoirs. So this is shown in illustrative form in figure A, with the micro resolution highlighted in yellow. And one thing you'll note is that the channel component is being modelled by just a single microelement, and we've deemed this acceptable because the channel height is constant along the channel length. So as long as the pressure variation is relatively linear, this should be a fine approximation. The boundaries are also highlighted by the dashed lines, and because it's a serial network, there are two boundaries for each component, because each component must have one inlet and one outlet. So moving on, figure B shows the setup for the full molecular simulation, and for this work we've chosen molecular dynamics to be the solver of choice, or also known as MD. The fluid is dense argon, the walls are comprised of frozen argon atoms, and all the molecular interactions are modelled with a simple Lennard-Jones potential, the parameters of which you can see in the grey box. Our method is compatible with more complex models, but for the sake of verifying our hybrid method, we decided we might as well use a simple model. The channel height is 3.4 nanometers, the length of the channel component is 102 nanometers, and this is an aspect ratio of 30. And it's actually quite a short channel for nanochannel, but we choose this size specifically to ensure that the full molecular simulation remains computationally tractable. The simulation is periodic in all directions, and the flow is driven by applying a body force to all the molecules in the shaded region, which you can see to the left of boundary 1 and to the right of boundary 6. And by applying a body force in this region, we induce a pressure drop over the main network domain. So looking a bit more closely at the GenIMM microelements, we can see that the reservoir components have been modelled in their entirety, and each reservoir component consists of the actual fluid reservoir and a small part of the channel, and this is to ensure that the flow through the channel is fully developed. Now each reservoir microelement also has an additional so-called artificial region attached to the component geometry, and this artificial region is shaded in figure C, and it has two purposes. Firstly, it enables us to use periodicity, and this means we don't have to deal with non-periodic boundary conditions, which are quite difficult in molecular dynamics. And secondly, we can apply a body force in this artificial region, which produces a pressure drop over the main component geometry, much in the same way we do for the full molecular simulation. So the channel microelement at the bottom of this figure is obviously much shorter than the main channel component, and the length of it is 4.08 nanometers, which is 25 times shorter than the actual component. So we perform 3 test cases on this network, and for all test cases we choose to constrain the mass flow rate through the network, and we do this because this probably best demonstrates the design aspect of the GenIMM, because the mass flow rate is a quantity you wouldn't be able to fix in a full molecular simulation. We also choose to fix the inlet pressure, or the pressure at the first boundary, in all cases. So for case S1, the main output of the hybrid method is the outlet pressure, or the pressure at the 6th boundary. For case S2, the main output is the channel height, or the height at boundaries 2, 3, 4 and 5. And for case S3, the main output is the channel length. That's the component channel length, not the microelement channel length, which is fixed, of course. So we obviously don't know the initial values for these, but we have to make a guess at them, a prediction, in order to actually perform the first iteration of simulations. So we make an intentionally poor guess with around a 60% error to the actual final value from the full molecular simulation, in order to show that our method will still converge even if your intuition is way off. Moving on to look at some results, you can see that all three cases converge after 3 iterations to a fairly tight tolerance of 0.02 and then remain numerically stable after that. And this represents a speed up over a full molecular simulation of around 4 times. And this speed up is quite modest, but you've got to remember that the network we had to make quite short so that a full molecular simulation remains computationally tractable. And also this doesn't account for the fact that if you wanted to use a full molecular simulation to gauge the geometry which should give you the mass flow rate and the other macroscopic properties that we want to specify, then you need to undergo some kind of trial and error process, which our method avoids. So looking at the errors at convergence for all cases, the mass flow rate, the pressure at all boundaries, the channel height and the channel length, depending on which properties were allowed to vary in each case, they were all less than 1% away from those properties measured in the full molecular simulation. And this is highly accurate. You're not really going to be able to get any more accurate using molecular dynamics because of the noise inherent in it. And it's obviously a lot more accurate than the initial predictions, which were 60% out. So finally, I'd like to further demonstrate the accuracy of our method by looking at some profiles. Firstly, streamwise profiles for pressure and density, and you can see that in the reservoirs the GenIMM solution is very accurate compared to the full MD solution. In the channel it's not quite as accurate, and this is because the GenIMM solution assumes a linear pressure drop along the channel, and this clearly isn't quite the case for the full MD, but it's near enough that the GenIMM it gives a good approximation and it doesn't affect the accuracy of the results at any of the boundaries. And secondly, I'd like to look at the transverse profiles for velocity and density. And these highlight the fact that the GenIMM doesn't just accurately model the mean macroscopic properties at various points along the channel, it also captures the non-continuum and non-equilibrium effects that dominate the flow behavior at the nanoscale. So if we look at the velocity profile on the left, you can see it accurately models the velocity slip at the walls, and in the density profile on the right, it accurately models the molecular layering effect. So this is the end of the presentation, and hopefully I've shown you that these hybrid methods can be used as a design tool as well as a simulation tool, because they are more efficient than a full molecular simulation without really losing any accuracy.